It's okay, let's just skip that.
All right. It still looks crooked. And now it's less so. Okay. So, next unit. Wow, we have just a few units left. Sound and waves, wave mechanics and then sound. So there's a reason we're doing wave mechanics after harmonic motion, and there's a reason we called harmonic motion harmonic motion. Some of you heard like harmonic, that's what my band teacher says. He says, you guys couldn't be less harmonic than, you get the idea. So harmonics are simply vibrations, things that bounce back and forth. Just like a pendulum that shifts back and forth, when a piece of metal vibrates back and forth, it causes the air around it to vibrate back and forth. So you don't see it unless you're really close, but you can actually see the tines of the tuning fork actually blur a little bit as they go back and forth. And it's causing the sound, it's causing the air around it to vibrate. Yeah, like that. Yeah. No, this is totally cool. So we're going to start talking about general wave properties, the difference between a transverse and a longitudinal wave, and then we will transition into sound waves specifically. Okay, so two wave types. What do you call it when the little dots are moving perpendicular to the travel of the wave? Transverse. A transverse wave is usually what we see in a sine wave. Okay. In fact, if you take a pendulum or a spring and you attach a little pen to it and then drag it along, it'll actually create a sine wave. So if the object medium is going up and down and the wave is going across, you get a transverse wave. So if I go like this and I move across the room, you can see it maps out a transverse wave.
This looks like those, the bottom one is just rotating.
You know, they're actually just going boop, 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 boop. And these are going boop, 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 boop,
No, but it looks like it's going in like a circle, like rotating.
Oh.
That's sweet.
Yeah. Look at that. I could look at that all day, man. All right. So a transverse wave, transverse literally means across the path. So it's moving transverse across the path. A sine wave is a transverse wave. Light waves are transverse waves. Okay. And transverse waves, or the study of optics and light waves, are not what we're talking about in this unit. We're going to talk about the kind of wave that moves with the medium, in the same direction as the medium. What do we call those? Longitudinal waves. Good. Oh, sorry about the color. So longitudinal waves are waves that move parallel to the medium or with the medium. So you can actually see the wave cruising along from left to right, and if you pick your favorite molecule, it just goes back and forth and back and forth and back and forth and back and forth and back and forth. Longitudinal wave. Now, sound waves are longitudinal waves. And that's what we're going to spend most of our time thinking about sound waves.
It just moved back and forth.
Yeah.
Yeah, that one looks really weird. It's all moving forward.
Yeah, I mean, unless you're the dragonborn, when you talk, the air basically stays put, but the sound waves travel through the air. So when I'm talking to you right now, my sound waves are causing the air to vibrate back and forth. It's going. So the molecules are just going like this, but as they slam into additional molecules, they're sending my sound waves across the room at about 400 miles per hour. I mean, 400 meters per second, about 700 miles per hour. Yeah, so unless you're the dragonborn, then the air mostly stays put when you talk. Now the biggest difference between a transverse wave and a longitudinal wave, the transverse wave is something we save for physics AP 2, we save for optics. A transverse wave can exist without a medium. It can exist. It can travel through a medium, but it can exist without a medium, which is why that big ball of fusion out in the sky, why it warms us up and lights the area, because its waves can travel through space. There's not much going on between the sun and the earth. Not a lot of medium. But there's a lot of air in the room. And my longitudinal waves or my mechanical waves require a medium. It's like they say, in space, no one can hear you scream.
He's coming at you with a knife. Doesn't make sound.
Well, as
There's be a horror movie in space where they're all trying to scream.
There probably is. Yeah. So if you forgot your helmet, you're going to open the door to your spacecraft. You forgot your helmet. You're going to like, oh. And no one's going to hear you say anything. Then you run back inside because you don't have any air in your lungs anymore. Oh, and just in case you were wondering, if you did open the door to your spacecraft and there was no air out there, you would not immediately die. Just get back in, close the door.
Really? So that's why Princess Leia survived? Arrow Organa, man, she was
Oh, is that the newest movie?
Yeah.
Spoilers! Some of us are waiting for the Blu-ray. It's okay. Yeah, I really don't care. Yeah. Okay, so yeah, Guardians of the Galaxy is probably a more accurate explanation. Hold your breath, you'll be okay. So sound and light, just a quick difference between sound and light. Sound are longitudinal waves. They need a medium to travel. They travel at about 340 meters per second, which is about 700 miles per hour in air. Light waves are transverse waves. They do not need a medium, and they travel at 300 million meters per second, 3 times 10 to the 8th meters per second. And again, the study of light waves is a whole unit in optics and electromagnetism, which we're not going to get to unless you take physics next year. So we're going to focus on what are called mechanical waves, which are longitudinal waves. So what's actually going on when I'm talking to you? There's a number of things going on. I'm vibrating my vocal cords, much like you pluck a guitar string. I'm vibrating my vocal cords. My entire skull is vibrating, and sound is coming out from my face. Just like when you pluck a guitar string, the entire body of the guitar amplifies the vibrating sound, and the sound comes from the body of the guitar. So that's what's happening. And then the air immediately around my face is vibrating. And it's vibrating back and forth. And those vibrations are propagating through the air until eventually they end up in your ear. And what happens in your ear is your eardrum vibrates sympathetically. Sympathetically. Like if you feel sympathy for someone, you'll share their emotions. Well, your eardrum vibrates sympathetically to the vibrations coming out of my face. And then your brain, because most of you grew up around here, interpret those crazy vibrations as words. You know what's really fun?
What?
I can't hear this, but you can. Because my eardrum is a lot older than yours, so it is less elastic than yours.
You really can't hear that.
I can hear I can hear the sizzle of the air of the water vapor around this I can hear the sizzle of this thing, but I can't hear the really high pitched capacitors discharging.
It's like a dog whistle.
Yeah, it's like a dog whistle for teenagers. But as you age or abuse them, as you age or abuse, your eardrums become less elastic. So I can't hear that high pitch. I probably top out somewhere around 8,000 or 9,000 hertz. You probably top out somewhere around 12 to 15 hertz. 1,000 hertz. So when you're talking to your old geezer parents and she's like, eh? What you should do is talk lower. Lower. Especially if you're a girl. You're like, Grandma, can you give me $100? She's like, eh? And you're like, Grandma, can you give me $100? Oh, sure. Okay, so what do waves do? Waves carry energy. Okay? Waves carry energy. The air molecules that are sped up as the waves travel through you carry the potential energy that I've used in my vocal cords. So waves carry energy. There's a third type of wave called a surface wave, which is a mechanical wave, so it does require a medium to move. It is a mechanical wave. But a surface wave is a combination of a transverse and a longitudinal wave. If you take geology, you'll learn all about them. But I'm not going to talk about them here. Yeah.
I like how you have them books and they're really cool.
Yeah. Dan Russell, Kettering University, used without permission.
You have to take this PowerPoint down.
I know. Google's not going to allow me to upload it. Oh, can I get, like, sorry, you have the thing in there. No. I'm sure he or she would be fine. It's Dan. Happy birthday to Dan. Okay, so a surface wave is a combination of a transverse and a longitudinal wave. It is a mechanical wave, so it does require a medium. Okay, two ways to make a wave. First way to make a wave is a pulse, a single thud. Okay. Yeah, exactly. Like when you hit the table with your fist, you're like, bonk. That wave pulse propagates out through the table. Okay. Wave pulse. Pulses usually create longitudinal waves, mostly because light waves usually require multiple crests and troughs to be seen. The other way is through resonance, vibration, or simple harmonic motion. Again, this is harmonic motion. The tines of the tuning fork are vibrating back and forth with the same frequency constantly. Their amplitude is decreasing to the point where you can't hear it anymore, but once I strike it, they're going back and forth and their frequency is pretty much constant. So it's harmonic motion, simple harmonic motion, vibration, or resonance.
You're abusing my ears.
You're abusing my face.
I need a baby now. You're abusing my eyes.
You're abusing my common sense.
Oh.
You're abusing my sense of decency. Are you upset because you're in a battle of wits and you're fighting unarmed?
Yes.
Yeah. Okay, so questions so far? All right. Oh, don't go? Okay. Give you another minute or two.
Feel free to just shoot me.
No. I wouldn't want to waste the bullet. Okay, so ready to move on? Okay, no questions? Then we move on. Okay, so I'm going to represent the first type of waves. I'm going to show you a transverse wave because transverse waves make it easiest to see the different parts of a wave. So the wavelength is the difference between successive crests or successive troughs. And again, I apologize for my projector not being terribly bright. Can you see this in the back? Can you see the wave in the back? Okay, let me just, yeah, okay. I'll just draw it over on white. So there you go. Or even better, let's draw it over here. Okay, so there's that's a really ugly transverse wave. The wavelength is the length between successive crests or successive troughs. Okay. A wavelength is the distance between successive crests or successive troughs. Yeah. That's the easiest way to make a wave is just go up and down and then walk around. So that is a wavelength. Wavelength is given the Greek letter lambda. I don't know why, it just is. Maybe it's for length. So the distance between successive crests or successive troughs, or the distance until one wave repeats. So if you start the wave here going down, you end the wave here going down. So this would also be a wavelength. So the difference between successive crests or successive troughs, or until the wave repeats. Trough's the bottom. Trough's the bottom, crest the top. Yeah.
So like the heartbeat readers of the transverse waves?
Yeah, yeah. Yeah, so when someone puts a little thing on your finger to get the pulse, this is different than the oxygen content. Basically what it's doing is it's measuring differences in pressure over time. So it's like high pressure, low pressure, high pressure, low pressure. So they're not so much waves like we're learning. They're just data. But if you do want a sinus rhythm, they call a sinus rhythm when you have a good steady up and down. It's sinusoidal. Sinus rhythm?
Like sinuses?
No, like sine, like the sine wave. And then if you get into asystole, that's when you go beep. That's called asystole, meaning you have no pressure difference between the high and the low. Asystole. Okay, period is the time for one cycle. Now, if you are graphing energy versus time, then this lambda is going to be period. If you're graphing energy versus distance, let's say distance, then we have wavelength. So this exact same wave, if we graph it versus time, would be period. So the period is also the distance from successive crests and successive troughs, or until it repeats, when the graph is graphed for time, not distance. Do you understand what I just said? Okay, I'll say it again a little bit slower. If my graph is energy in the y-axis and time in the x-axis, what I'm graphing here is period. If my graph is energy in the y-axis and distance in the x-axis, what I'm graphing here is wavelength. Okay. But if you had a graph just thrown in front of you, then you need to know what the axis would be to determine if you're looking at wavelength or looking at period. Okay. And of course, if we're talking about period, we're also going to talk about what?
Frequency.
Frequency, exactly. Frequency is the inverse of period. So it's a mathematical inverse of period, just like we talked about in the last unit. So I know this tuning fork to have a frequency of 400 hertz. Since it's an audible frequency, we call it a pitch. So my tuning fork has a frequency of 400 hertz, meaning those little tines are vibrating back and forth 400 times a second, which is why they just look blurry. So you have a tuning fork, you strike a tuning fork. Never strike a tuning fork with something hard unless you miss. I was going for this. Okay, so when you strike a tuning fork, the tines are kind of blurry because they're zooming back and forth. This one has a hertz of 426 hertz. Yeah.
What happens if you strike it hard and you miss?
Then you hit the table. You could actually chip the tuning fork. Some of these tuning forks are really badly chipped. Like the ones you're going to be using in your lab are these really slick cases of tuning forks.
Does it hurt?
Made from the finest 10-year-old craftsmen in China. And some of them, people, no matter how many times I tell you never hit a tuning fork, never hit a tuning fork with a tuning fork, people still do it because it sounds cool, and there's little chips in a lot of the tuning forks. So you're like, it says 343, but I'm getting 348. That's because it's broken.
What does it sound like though?
Is there a safe way to do it?
No, there isn't.
That's not good.
Yeah, that's not what you're supposed to hear. You're supposed to hear this. So that cling is actually some serious nasty reverberation coming from the tuning fork. And these are small tuning forks for a reason. They're small tuning forks for a reason that I'm going to tell you when we do the lab.
They're cheap.
No.
Smacking each other.
No. Something actually specific to a classroom, yeah.
When are we doing this lab?
Pretty soon. Probably Friday. Okay, so amplitude is wave energy measured from the equilibrium point to what is called the crest or the trough. Okay. So it is the intensity of the wave, it is the volume of the wave, it is the loudness of the wave, it is how much wave energy is being carried by the wave. And it's measured from the equilibrium to the crest or equilibrium from the trough. One of those pitfalls a lot of people will fall into is they'll measure from the top to the bottom. Or an exercise may even give you the amplitude from the crest to the trough. That is not the amplitude. From the crest to the trough is 2 amplitudes. You got to divide by 2. So in this case, in my example, you pick a medium point right there, and the amplitude is the distance from the equilibrium point to the crest or the equilibrium point to the trough. Amplitude, amplitude. Okay. How we doing so far? Got the lingo? Moving on? Moving on. All right, so I have some questions for you. I have 3 standing waves. Standing waves are pretty cool. A standing wave, and you're going to actually build some. A standing wave is created when you have a vibration source that is constantly creating new vibrations that are basically amplifying the existing vibrations. So they're overlapping with each other. Okay, I'm going to turn the lights on so you can see this. If you want to make one of these, they're really simple. You just take apart a PlayStation controller, and then you solder a 9-volt connector to it. So all this is a PlayStation shock cruising around. Yeah.
That thing that happens when you get shot, like.
Yeah. All a PlayStation shock is a motor with a half circle thing.
Well, what do you know? I already have a PS3 controller.
Exactly. Yeah. So you have. See, it's right there. So I just took apart an old PlayStation controller, and then I soldered a 9-volt battery connector to it. So this is a standing wave. You can see this? Yeah.
With the white background.
I have one with yarn, but you're actually going to build some with 2. Now watch what happens if I get beyond what's called the natural frequency or the fundamental frequency. The wave just disappears. But there's a point where I can get another wave right there.
Oh.
Yeah.
Why is this happening?
Because the wave energy is going up the string, hitting my thumb, and coming back down. Up the string, hitting my thumb, and coming back down. And the wave energy wants to spread out because the universe is chaotic. So it spreads out into a transverse wave. Now, if I don't have the fundamental frequency, the wave basically just disappears. If I get to the fundamental frequency or a multiple of the fundamental frequency, then I get a wave. This is called a standing wave.
Could there be 3 of those things?
There could. I would need to sit on a chair or stand on a chair. Thank you. Hey, stop moving down there. There we go. Now we're going to talk about there's your fundamental distance, or fundamental wavelength, right about there. And then a multiple of that, we'll go twice that length. There you have 2 times the fundamental. And then down here, we're going to get somewhere around 3 times the fundamental. Right about there. You're going to do this in a lab, by the way, with far more sciencey pieces of equipment. We have really cool resonators that we bought last year to do this very thing. And you're going to investigate what happens when you change the tension of a string, what happens to its wave speed and wavelength. Okay, so I have a question for you. Actually, I have 3 questions for you. I have 2 waves. Ladies and gentlemen, I have 3 waves. I have 3 waves shown up here labeled A, B, and C, lifted from your textbook. And I have some questions for you. Which wave has the greatest amplitude? A. Yeah. A has the greatest amplitude because you'd basically pick a point at the equilibrium, and you'd measure the distance. So the biggest difference is the biggest amplitude. So yeah, A has the biggest amplitude.
Would A's amplitude be twice the size of B's?
I would have to measure. And since I don't know how to measure things, I can't say. Which one has a wavelength of 2 meters? If the distance between the anchor points are 1 meter, which one has a wavelength of 2 meters?
I'm going for the wild card, C.
C. It's not C. Okay.
Oh, it would be. Wait.
Okay, let's take a vote. Who says it's A? Who says it's B? Interesting. So only somebody has to be contrary. So I'll say it's B. Let me point something out and see if you want to change your answer. In order for a wave to exist, you must have a crest and a trough. You must have a crest and a trough. So, who thinks it's A? Ah, yes. Who thinks it's B? It is B. B has a wavelength of 2 meters. So you have to have an entire crest, an entire trough. That one has a wavelength of 1 meter. Oh, did I say 2? I'm sorry. It's A. So this one has this one, and then another wave over here. Is my face red? Yeah, I meant to. I thought it was asking for 1 meter. But most importantly is A has a wavelength of 2 meters, B has a wavelength of 1 meter, and C has a wavelength of 0.6. Right there, 0.6. 2/3. Okay. Which wave has the greatest frequency? C. Yeah, C has the greatest frequency. Okay. Hey, formulas. We love formulas. So frequency is still the inverse of period. Frequency is still the inverse of period. Wave speed. This is interesting. People speed has what unit? Meters per second. Okay. So people speed, if we're going to determine how fast you're going,